Next, we're going to look at coordinates in three-dimensional space. So the three-dimensional coordinate system is formed by passing a z-axis perpendicular to both the x and y axes at the origin. And this is a rough representation of what that looks like. Notice there are three primary planes: the xy plane, the xz plane, and the yz plane. Points are represented as ordered triples x, y, z, where x equals the directed distance from the yz plane to a point P, y is the directed distance from the xz plane to a point P, and z is the directed distance from the xy plane to a point P. This is an example of a couple of points plotted in the three-dimensional coordinate system, and I'm going to be honest with you, some of these are a little bit difficult to visualize. So the point -2, 5, 4 goes -2 for x, +5 along the y-axis, and +4 up and down for the z-axis. And you can kind of figure out the rest of these in that same way. Now the good news is a lot of what we've done can be extended very easily to 3 space just by considering the z. So the distance formula here is the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. We're just throwing on that extra little piece for the z coordinates. Midpoints, same thing, z1 plus z2 over 2. So if I want to find the midpoint and the distance between 2 points, I can do that pretty easily. The midpoint is just going to be averaging the x coordinates, 3 plus 2, averaging the y components, -2 plus 0 over 2, and averaging the z's, 4 minus or plus -5 over 2. And so I get 7/2, -1, and -1/2. And if I want to find the distance, and I have no idea what this a is right here, just ignore that. The distance would be the square root of, let's see, we're going to do 4 minus 3 squared plus 0 minus -2 squared plus -5 minus 4 squared. So that's the square root of 1 squared plus 2 squared plus -9 squared, which is the square root of 1 plus 4 plus 81, or the square root of 86, and that cannot be reduced any further. Instead of equations of a circle in 3 space, if we have all three of these x minus x0 squared plus y minus y0 squared plus z minus z0 squared equals r squared, this forms a sphere or a ball. And basically what you're going to be looking at as if you're given 2 points that are a diameter in points, your r is going to be 1/2 of that, and your center is going to be the midpoint of that. So r will be 1/2 the diameter, which is 1/2 the distance. And of course we just found the distance, which is the square root of 86. And the center is the midpoint, which we also just found in the last problem for these 2 points, 7/2, -1, and -1/2. So the equation would be x minus 7/2 squared plus y minus -1 squared plus z minus -1/2 squared equals 1/2 times the square root of 86 squared. Or if you just square that side, you get 86 over 4 or 43 over 2. So that would be the equation of the sphere with 2 of those points as the endpoints of a diameter. Another concept that extends to 3 space are the standard unit vectors. So the 0 vector, of course, is the vector containing the coordinates 0, 0, 0, 0 for its components. And keep in mind this is a vector here. I is 1, 0, 0. J is 0, 1, 0. Those are both in the xy plane here. K is the unit vector along the z-axis, so that's going to be 0, 0, 1. And anytime you have a vector in 3 space, v1, v2, v3, that's going to be v1i plus v2j plus v3k. The standard unit vector notation for a vector v. vectors in space. Two vectors, u and v, are equivalent if and only if u1 equals v1, u2 equals v2, and u3 equals v3. The component form, if v is represented by the directed line segment from p to q, then v equals q1 minus p1, q2 minus p2, and q3 minus p3. All of these are extensions. The length, you can just tack that plus v3 squared on the end of that, inside that square root. The unit vector in the direction does not change. It's just 1 over the magnitude times the vector. And the vector addition, same thing. You just add up the components. Scalar multiplication, you just got to distribute that scalar multiple through all 3 components. Now, one thing that's very important to understand about 2-space versus 3-space is context. So we saw an example when we were talking about 2-space where the I component was 0, and so the vector was just 6j. Now, it's understood in something like that even though there wasn't an I written there, there could have been. Okay? So you can add, if you just are looking at adding 2 things like 3i plus 2j plus something like 3i minus 4j plus 2k. Okay? In this one, it's understood that the k vector has a 0 out front. So with this one, you would add and you would get 6i minus 2j, we're just adding our like terms, plus 2k. Okay? But if you have something like this, you cannot add 3, 2 plus a 3-space vector 3, negative 4, 2. Now I know these represent the same vectors, but this is strictly a 2-space plane vector. This is a 3-space, 3D space vector. So these 2 are not defined to be added, but with this one, the context is if you're being told to add it, you can assume that you can, because it's understood to have a 0 coefficient on the k. So just some little bit of notation, you can't add these 2. Okay, so for this example, it doesn't give us instructions. Let's find for part A the component of v, and then we'll write it as a linear combination of I, j, and k, and we'll find some other stuff. We'll get there. So v in this case is going to be, it's from this point to this point, so we'll have 2 minus 4, we'll have 4 minus 2, and we'll have 3 minus 1. So this gives me negative 2, 2, and 2. If we want to write v as a linear combination, of I and j and k, v would be negative 2i plus 2j plus 2k. If we wanted to find the magnitude of v would be the square root of negative 2 squared plus 2 squared plus 2 squared, which is the square root of 4 plus 4 plus 4, or the square root of 12. And remember, you can reduce that by dividing repeatedly by prime factors until you find a repeat, and then you just bring that out once as 2 square root of 3. I do expect to see those reduced. And finally, let's find the unit vector in the direction of v. So u would be 1 over 2 square root of 3, and let's leave it in component form, which was negative 2, 2, and 2. So that gives me negative 2 over 2 square root of 3, negative 1 over square root of 3, 1 over square root of 3, and 1 over square root of 3. And then if we rationalize that, we get negative root 3 over 3, root 3 over 3, and root 3 over 3, multiplying by root 3 over root 3. two non-zero vectors u and v are parallel when there is some scalar c such that u equals c times v. So it says show that z equals 3, 2, negative 5 is parallel to the vector negative 6, negative 4, 10. So I can observe that negative 6, negative 4, 10 is equal to negative 2 times 3, 2, negative 5, because if I distribute that, I get this vector. So v is equal to negative 2 times that vector. So that means that they are parallel. If that's not the case, if they're not in proportion to each other all the way across, then they would not be parallel. If two vectors v from P to Q1 and w from P to Q2 have the same initial point and are parallel, then the points P, Q1, and Q2 are collinear, meaning that a single line can pass through all three at the same time. So this is to determine whether the points 1, 2, 4, 2, 5, 0, and 0, 1, 5 are collinear. So I'm going to first find the vector P, Q1, and we'll call this one P, Q1, and Q2. So this would be 2 minus 1, 5 minus 2, and 0 minus 4, which would be 1, 3, negative 4. PQ2 would be 0 minus 1, 1 minus 2, and 5 minus 4, which would be negative 1, and negative 4. And actually, I'm sorry, 5 minus 4 is 1. Crazy. Okay, so I'm looking at these two vectors, and neither one of these is a multiple of, these aren't a multiple of each other. There's no way that they're in proportion to each other. And they have the same initial point. So this means that P, Q1, and Q2 cannot be collinear, because we know that these two are not parallel. Now let's look at another example. Here, if we let this be P, Q, and Q1 and Q2, PQ1 would be, see, 3 minus 0, 4 minus negative 2, 4 minus negative 5 is 9. PQ2, 2 minus 0, 2 minus negative 2, and 1 minus negative 5. So I have 3, 6, 9, and I have 2, 4, and 6. Now these I can see are in proportion to each other, because we could multiply, for example, PQ2 by 3 halves, and we could get PQ1. So that means that these two are parallel. And since they have the same starting point, that means P, Q1, and Q2 are collinear. They all exist in a single line. One last example I want to point out is this one, v equals 3j minus 5k. It says find the magnitude of v in a unit vector in the direction of v. So it's understood that this particular vector has a 0 for the I component. So this is existing in the yz plane because x is going to be equal to 0 for every point in the vector. So in component form, that would read 0, 3, negative 5. The magnitude of v is going to be the square root of 0 squared plus 3 squared plus negative 5 squared, which is the square root of 9 plus 25, or the square root of 34. And the unit vector in the direction of v would be 1 over the square root of 34 times 0, 3, negative 5, which would give me 0, 3 over root 34, negative 5 over root 34, or 0, 3 root 34 over 34 when I rationalize, negative 5 root 34 over 34. And again, depending on the context, you may want to write that in the IJK form, which would be 3 root 34 over 34j minus 5 root 34 over 34k. We can leave the 0i. You can write it, but you don't have to.